Hi everyone! In this video we're going to be talking about section 10.6, which is on the alternating series and conditional convergence. Okay, so we've been talking a lot about series up until this point, so let's continue specifically looking at what's considered an alternating series. So by definition, an alternating series, so you might already kind of guess where I'm going with this, has terms that are alternately positive and negative. Alternately positive and negative. So if one term is positive, the next term is negative, and vice versa. Okay, so that's what it's called, an alternating series. So first example, a series that we've been looking at in progression. So we started by looking at the sequence that was considered the harmonic sequence. Then we looked at the harmonic series, which is when you add the terms of the sequence. Now, the alternating harmonic series. Okay, so before I write it, let's see if you can kind of think about what this is going to look like. So I'm going to write it in my summation form. So the summation from n is 1 to infinity. Harmonic series, hopefully that's the part you remembered. It's 1 over n. Okay, the summation of the terms 1 over n. But what makes it alternating is if I change the sign, positive and negative, between each term. And so the way we adjust for that is we have -1, and we're going to write to the n plus 1 power. Okay, and let me just write out a few terms so you can see that this is true. When n is 1, this power is going to be 1 plus 1, so 2. So this is going to be -1 squared. So I'm going to write it as +1. Okay, +1. And then my n value was 1. Okay, +1 times 1 over 1. My next term, because remember we're adding the terms of a sequence to get a series, so I'm just going to put a plus sign, and I'll adjust in a minute to if it's going to stay plus or turn to a minus. When n is 2, this is going to be a third power, so something negative to the third power is going to stay negative. Okay, so that's going to be -1, and then n was 2, so 1/2. And then plus, let's do a couple more. When n is 3, this is going to be a fourth power. Something negative to the fourth power turns positive. So +1, and then our n was 3. And let's do one more. Plus, when n is 4, this is the fifth power. So this is negative. And then n was 4. ... Okay, so let's just make this look a little nicer. 1 times 1. -1 times 1/2, 1 times 1/3, -1 times 1/4, and so on. Okay, so this is our first example of just what an alternating series looks like. Specifically, this is the alternating harmonic series. One term is positive, the next is negative, or we start negative and go positive, but then it alternates signs. All right. So we are going to look at a test, which is called the alternating series test, for does an alternating series converge or not. So let's do that now. So here is the alternating series test. This is a test to see if an alternating series converges. Okay, so does this series converge to a value, or does this sum when you add go to like infinity or something like that? So the series, notice we have our -1 to some powers. Depending on n, this is going to turn into a positive or negative, and then times u sub n. So u sub n, just think of it like you've been thinking of like a sub n. The only difference here is that u sub n, we're calling it the absolute value of a term value, because we want to make sure that the -1 here, the power on this -1, affects the overall sign. Okay, so if we're saying that this is already positive, then the only thing that's going to affect these signs is this -1 to some power. Okay, so just a minor distinction there. So our alternating series converges if the following 3 things are true. So let's talk about them. First, all of the terms have to be positive, greater than 0. Okay, so all of your terms of this series are positive, and that's before you consider the minus sign. Okay, so that's what I'm saying. The u sub n is considered absolute value of a sub n. So this is positive, minus sign is not part of it, so we'll say this is positive, this is positive, this is positive, excluding the plus and minus signs. 2, u sub n terms are eventually non-increasing. What does that mean? It means that at some point, at some n value, your terms are starting to decrease, or they just stay constant. They're not getting bigger. And so one way you can look at this is you can say that u sub n plus 1, that's our notation for like the next term, okay, is less than or equal to u sub n. Okay, so let me throw some numbers in there so it makes more sense to you. You can say something like the 5th term is less than or equal to the 4th term. Or if you want to flip it, this is saying the 4th term was bigger than or equal to the 5th term. The previous term was larger, meaning the next term is getting smaller and smaller and smaller. So non-increasing, okay, or equal, or they could stay the same. Then part 3 here, notice what this notation is saying. There's no summation here, so this is the sequence. This is saying that the sequence has to go to 0. The sequence that your terms come from, so the sequence u sub n converges to 0. So remember, there is a difference. Converges to 0. Sequence, you're just listing terms. So if I were to just list the terms, okay, like just list, that's the sequence. That has to go to 0, according to part 3. Series is when I'm adding the terms. So plus this, plus negative this, plus this, plus negative that, and so on. So just a minor distinction there as well. So this is our alternating series test. All 3 things have to be true. If they are true, our series converges. So we're going to check in an example that all 3 of these are true. If they aren't, we can say that it diverges, or if they are, we can say it converges. Let's take a look at this example. So we already talked about the alternating harmonic series. So I want to know, does this series converge? And I left our test over here, most of it. It converges if the following 3 things are true. So we're going to check those 3 things for this series. So number 1, are all of the terms positive? Okay, remember the u sub n is the absolute value of the term because the minus sign comes from the different powers of -1. Okay, so for us, let's just list this out. I already wrote part of the terms, but term 1 would be 1. Actually, I'll write it down here next to bullet number 1. So term 1 is 1, term 2 is 1/2, term 3 is 1/3, term 4 is 1/4, and so on and so on. They are all greater than 0. So yes, number 1, good. All right, number 2, are the terms eventually non-increasing? Are they eventually staying the same or eventually decreasing? As long as they're not getting bigger, okay? So again, from the terms, okay? Let me write it, I'm going to go right here. So we're looking at part 2. We have 1. 1 is greater than the next term, 1/2. 1/2 is greater than the next term, 1/3. 1/3 is bigger than 1/4, and so on. So the previous term is greater than the next term, meaning that these terms are actually decreasing. So that's good. Number 2, check. Third part, is the sequence of these terms going to converge to 0? The sequence, not the series, the sequence. You might already know this. Hopefully you remember from previous videos. Yes. And I won't just say yes and check it off. Let me show you. So yes, it is, if you recall, that our harmonic sequence, the sequence of the terms 1/n, does converge. And you can check that by taking the limit as n approaches infinity of the sequence, 1/n. 1 over a huge number like this is 0. So yes, This does converge to 0. So all three things are true. So what you can say is, does the alternating harmonic series converge? By the alternating series test. I'm just going to abbreviate. Alternating series test. Yes. The series converges. The series converges. So it's just a test to check. And if we checked and everything checked out, all three parts, yes, this series converges. So, not so bad, hopefully. And if you just go through these three parts, you'll know whether or not your alternating series converges. I'm going to show you a little bit about the difference between the sequence and this series, and then our regular harmonic series, not the alternating one. So you can kind of piece it together, because we've been seeing this sequence and then series show up quite a bit in previous videos. So let me just kind of wrap up this sequence for you in the corresponding series. Alright, I want to just show you a little bit about the harmonic sequence and series, just so you can get a feel for it, especially if you are more of a visual person, what's happening with the three different ones we've seen with the 1 over n involved, the sequence and series. So the first one was our sequence, way back at the beginning of this chapter. So our sequence is just a list of terms where n comes from the term number, so 1 over n, 1 over 1 is just 1. 1 over 2 is 1/2, then 1/3, and so on. So I'm just going to plot these points so that you can see it visually and why this one converged. We just wrote down that this converged to 0. Here's why. So if I plot the points, let's go to blue. When I plug in 1 for n, I get out 1 for a sub n for my sequence. When I plug in 2, I get out 1/2. When I plug in 3, I get out 1/3, which is a little lower than 1/2. When I plug in 4, I get out 1/4, a little bit lower, 1/5, a little bit lower, and so on and so on and so on. So eventually these terms are approaching 0. So that's why this one converged. So converges to 0. Okay. The next one was our harmonic series, when we started adding up these terms. If you remember, this one did not converge. It diverged. So let's see why. Notice this notation is the partial sums. So when I'm starting to add the terms. So the first term, when I plug in 1, is just 1 over 1. When I add that to nothing, it's just still 1. Okay? So first sum is 1. First partial sum. So if I plot that, 1. When I say my second partial sum, that's 1 plus the next term, 1/2, which is 3/2. This is 1.5. So it's actually higher. Okay, so it's a little bit off my graph here, not quite to scale, but going up. Then the next term, that will be 1 plus 1/2, or the next partial sum, 1 plus 1/2 plus 1/3. That one's 11/6. Okay, so that's about 1.8. Okay, so plug in 3, I go even higher, about 1.8, and you can start to see what's happening. So if I give you more terms here, more partial sums, you'll see, I'll just give you the values. 2.1 about, the fifth partial sum, 2.3. So it's diverging. It's increasing, it's going to keep going to infinity. So this one, the harmonic series, diverges. Diverges. Let's see if I can write that correctly. Yeah, so that one did not converge. All right, and there's a visual for why. It's going to just keep going. We just found out that the alternating harmonic series did converge. So the harmonic sequence converged, the alternating harmonic series converged, but the harmonic series that was not alternating diverged. So let's see what happens over here. So my first partial sum, it's just 1. So 1, 1. My next partial sum is 1, and then alternating, it becomes a minus 1/2. Not like this one, alternating, so minus 1/2. That's just 1/2, 1.5, 0.5, so 1/2. Okay, so that's about right there. Then the next one would be 1 minus 1/2 plus 1/3. So alternating my signs. And let's see what I got for that. That one's 5/6, so about 0.83. 5/6, so 0.83. Okay, so that might be about right there. Okay, let me just mark 1/2, 0.5. The fourth partial sum, so that would have been 1 minus 1/2 plus 1/3 minus 1/4. That one, what did I get? 7/12. So 7/12, which is about 0.6. Okay, so when I plug in 4, I got about 0.6. So about right there. And let's do one more. For 5, the fifth partial sum, I got 47/60, which is about 0.78. Okay, so that's about, remember this one was about 0.83, so 0.78 is about right there maybe. Okay, and what's happening is this series is converging. Notice where it's going. Even though it's alternating, it's actually converging. If we kept plugging in numbers, it's going to converge to some value here on our outputs, our y-axis. And we're not going to go into how we get this number right now, but just so you're aware, this number is natural log of 2. That's actually what this series converges to. But it does converge. So visually, this one's converging to some value. This one was diverging. This one was also converging to some value. Okay, so I just wanted you to visually be able to put that together. Now, because this same terms, the same type of sequence but turned into a series, has different behavior, this leads into what we're going to talk about now, which is conditional convergence. Okay, so conditional convergence, here's the definition: a series that is convergent but not absolutely convergent. So absolutely convergent is something we talked about previously, whereas if you take the absolute value of the sequence that you're taking the series of, does that converge? So a series that is not absolutely convergent is considered conditionally convergent. Conditionally. Squeeze that in there. Convergent. Okay? So the series we just looked at, the alternating harmonic series, it converges conditionally. And then I just showed you the images of the graphs, but here's why. So the alternating harmonic series converges conditionally because even though that series we just looked at converged, we figured out it converged by the alternating series test, the 3 parts that we checked were satisfied. So even though this converged, if you take the absolute value, so same series but I take the absolute value, it turns into our regular harmonic series, because absolute value of this term right here is just going to be 1, so I don't even need to write it. This regular harmonic series diverges. So that's what conditional convergence is about, that our series converges under certain conditions, but not always. So if it's not always or absolutely convergent, then it's conditionally convergent. So let's take a look at the P series and how this is affected by this whole concept. Okay, let's look at the alternating P series. So we have what would have been 1 over n to the p, but now we have our -1 to the power. This time it's going to be n minus 1, but let's just write out the first few terms. And so if n is 1, plugging that in, you're going to get a power of 0. So that becomes 1 on top, and then n was 1, so that's 1 to the p power on bottom, which is just 1. Then our next term, let's say plus, when n is 2, that becomes a first power on top, which is -1, and then 2 to the p. Okay, and then the next one, when n is 3, that's going to be -1 squared on top, which is +1, and then 3 to the p, and then so on. It's going to be -1, 4 to the p, and so on. Okay, so let's just write this out a little bit better. So where it looks like 1 minus 1 over 2 to the p plus 1 over 3 to the p minus 1 over 4 to the p, and so on. Just so it's very clear that this is an alternating series. Now, does this converge or diverge? Alright, well first of all, let me just clarify. P is positive here. It's some positive number that's the exponent. So let's apply our alternating series test and see what happens. So we're going to say, by the alternating series test, there was 3 parts. Check part number 1. Part 1, are the terms positive? Okay, the terms, the u sub n terms, so not including the signs. Remember the distinction. So we have 1 over 2 to the p, 1 over 3 to the p, and so on. Okay. Now for any p value, for any exponent on these numbers here, greater than 0, this is going to stay positive. So yes, all of these are positive. Check number 1. Number 2, from the alternating series test, are the terms non-increasing? So my first term is 1. My next term is 1 over 2 to some power. Just to show you, let me give you a couple of examples with p. Let's say p is 1. Okay, so that's 1 and then 1/2 and then 1/3 and 1/4. Well, this one's pretty clear. Yeah, this is non-increasing. It's actually decreasing, getting smaller. Let's try another one. That was p was 1. Let me show you when p is 2. When p is 2, first term is 1. 1 over 2 squared, that's going to be 1/4. 1 is bigger than 1/4. My next term, 3 squared, is 1/9. 1/4 is bigger than 1/9. And then my next term would be 1/16, and so on. So yes, that worked as well. Now I'm only picking certain powers so far, so let me show you what happens if I pick maybe a not so nice power. Let's go with 1/2. Okay, so let me just, let me move right over here so you can see it. So this time I'm going to pick an exponent that's a fraction. Okay, that actually represents a radical. So my first term is 1. My second term is 2 to the, I'll write it in steps, 2 to the 1/2. The next term is 3 to the 1/2 on bottom, 4 to the 1/2 on bottom, and so on. So that looks like 1. This is square root 2. This is square root 3 on bottom. This is square root 4. So let's see what happens with these numbers. Okay? I'll just use decimals so that you can intuitively understand this. Let me see what I got for the decimal values. So 1 over square root 2 is about 0.7. So 1 is bigger. 1 over square root 3 is about 0.6. So previous term is bigger. 1 over square root 4, this is 1/2, which is 0.5. Previous term is bigger. So for all of my examples of p that I chose, this sequence of terms was non-increasing. It was actually decreasing specifically. So check number 2. So for part 3 of our alternating series test, the sequence is from the terms u sub n. So the absolute value of the terms needed to go to 0. So that's going to be just 1 over n to the p. So then we can determine if this is going to go to 0 if we take the limit as n goes to infinity of 1 over n to the p. And for any number p, if I take something very large and plug it in here, the power p on it, it's just going to still be 1 over something big. Okay, so this is in fact converging to 0. Okay, so all 3 parts were satisfied. So by our alternating series test, this alternating p series converges. Okay, converges. But this is going to be considered conditional convergence, because if you recall, when it was not an alternating p series, when it was just regular p series, it only converged sometimes and it diverged other times. So let's clarify this. So now, if we consider the absolute value of this series, it just turns into our regular p series, and then we know this p series converges if p is greater than 1, if the exponent p is more than 1, but it diverges if p is between 0 and 1, to include 1. Okay, so we have to take that into account for our final answer here. So I'm not just going to say that this alternating p series converges, I have to add something to it. So it converges, we say absolutely, converges absolutely if p is greater than 1, because it converged anyway, and it converged also when we took the absolute value for p greater than 1. So it converges absolutely anytime p is bigger than 1. And then it diverged when p is between 0 and 1, but it converged when it was alternating series. So we say converges conditionally if p, actually if 0 is less than p, which is less than or equal to 1. Okay, so that's the difference between absolute convergence and conditional convergence when it comes to these alternating series. Last part for this idea of conditional convergence. or absolute convergence. Why we care about it is because of the fact that I'm going to give you right now. So one consequence of knowing whether a series converges absolutely or conditionally is this fact here. So if a series converges absolutely and not conditionally, then what you can do is rearrange the terms. So the terms can be rearranged, you can reorder the terms, and the sum will stay the same. So one good reason to be able to do this is because sometimes it's not very clear to be able to figure out what does this series actually equal the way the terms are written. So if I just started adding these terms in the order they're given, maybe I can't see a pattern and I'd have to just manually add them up. So if I can see some kind of pattern, I can actually maybe rearrange these terms, figure out what does this series actually equal. Because if you've noticed, we've been testing for convergence, but we haven't actually been finding most of the time what the converging value is. Like, what does this series equal? I know in the beginning of the video I told you that our alternating harmonic series converged to natural log 2, but I didn't show you why. I just said that that was the number. So we do want to be able to figure out what does this series equal, and this is one nice way to be able to do it. Alright, so that's it for this video. In the next video I'll go over the alternating series a little bit more and then show you how to estimate the sum of an alternating series.